All right, recording is rolling. Welcome to a new week, Tuesday, October 17th. You guys enjoyed a 3-day weekend. So my plan is to finish the textbook puzzles today. We've got a few of those left. I'll have those due on Friday. So you have a few days to hold on to those if you want to. Because I do want to get you guys your next take-home quiz pretty soon. Probably tomorrow, I'm thinking, and then give you guys a few days to do that. So probably have that one due Monday. So if it helps have your textbook puzzle work next to you, right? You have that available. Tomorrow, I do a do it on conceptual questions related to gravitation. Right, so have your laptops then. There is, here, I saw an email this morning, I know it's really tiny text here, a dual enrollment meeting in the cafeteria periods 2 and 6. Now, there was a spreadsheet sent around with a list of students on it. I only saw one of you guys in here, so I'll let you know. But maybe your 6th period teacher, if you think that could possibly apply to you, just double check with your 6th period teacher. Just see if you're on this list. Something about dual enrollment in the cafeteria. Okay. Thursday and Friday, I got a few activities and ideas lined up for you guys. But yeah, we'll take today and tomorrow and wrap up these puzzles and conceptual questions. Right. Oh, and then before I get going too far, how many guys checked out the solar eclipse over the weekend? You guys get to try out your, oh yeah, did you try this out, the camera? Oh, okay, all right, like a welding helmet? All right, yeah. Yeah, I guess that's enough eye protection. Okay, because I wouldn't be able to verify that myself. I'd have to Google that one, but all right. I did use these glasses myself. I was able to look straight at it. It actually pretty well matches my diagram. That's like pretty much what it looked like. Look up at the sky, except you couldn't actually see the moon. It was all like blacked out, but you could see that crescent sun right there, right? And then I tried this pinhole camera too, because I wanted to see like how well this worked. Right? And yeah, it did work. I actually got a photograph I want to show you guys because I just pointed my camera down through this eyepiece. This sliding feature ended up not really being important, like to be able to adjust it, because I thought, well, maybe it'll help focus the picture or something. That ended not really being the case. I think it's really important though that you get like this pinhole to be a circular shape, and it is just a little tiny pinhole that is punched with an ink cartridge. Right? But I think if I do this in the future with my classes, I'll probably just not have this piece at all and just have them cap it right here, because that would work like just as well. So maybe real quick pull up picture I got. Find this. Here we go. Okay. So there's looking down the eyepiece. Right. Zoom in here, and ooh, you guys see like that crescent sun? See that crescent sun? Ooh, yeah, right. So it's like an inverted image. Okay. So of course it's like right behind me. It looks like down at the ground, right? Down at the ground. So let's see that. All right. Okay. So what did I tell you guys the next one was? 2045, I think it was. Something. All right, let's look at these textbook puzzles. All right, so I know we're on like week 3 of this topic. So all the chapter 6 rotation stuff we did. I think we knocked out like 2 of these, chapter 7. I think the last one we did was number 67, Mimas. Right? Oh, that's right. Right, so number 71, satellite. A geosynchronous satellite is one that appears to remain over one spot on Earth, as shown in this figure. Assume that a geosynchronous satellite has an orbital radius of 4 times 10 to the 7 meters, something like that. Right. Geosynchronous. So to break down the word, right? Like geo could be like referred to a planet. Synchronous, something to do with time. Ooh, like it's time to the planet. Hey, like time to the planet's rotation. So if this is Earth here, they have it labeled Earth. Right? If Earth takes like 24 hours to rotate once, you guys think the satellite also takes 24 hours to revolve once? Right? That would be geosynchronous. Right? And then from the point of view of someone on Earth, if you're like, say, like look up a telescope at that satellite, well, it just appeared to be just hovering in the same spot all day. Right? The background stars might be moving around, but yeah, right? Relative to Earth. Right? Calculate the speed in orbit, you're probably talking about like a linear speed, like a tangential speed, right? Because I know what its angular speed would be. Its angular speed would just match the rotation of the planet. So for Earth, that would be like one revolution every 24 hours, right? And then calculate its time period. Right? I hope this was pretty close to 24 hours. They might have some like like 23.9 hours or something. Well, I guess we're about to find out because I haven't saw this one ahead of time, but something like that, right? So they gave us some numbers here. So 71. Okay, so here's Earth. We got this radial distance r to this satellite, right? And when we say radial distance, we're going from the center of Earth to the satellite, center to center. Okay? And so they tell us, they said r equals 4.23 times 10 to the 7 meters. One spot on Earth, speed. Here. Is that all they gave to us? Okay. Okay. So I'll say given. Okay. They did also give Earth, so I might add some stuff to that list, but just throw down some equations, and if it looks like we're missing something, we might have to make an assumption for Earth. Okay. All right. So do you guys remember orbital speed? Do you guys remember what the expression for orbital speed is? Take this one there. Remember this right here, orbital speed, right? So when centripetal force is being provided by a gravitational force, here's the answer to your lab centripetal force. Here's Newton's universal gravitation. If you solve for speed, you get like this expression right here. Do one way to do it. Okay. Another way to get speed, or so we'll try this from a couple of different points of view, right? Like if we plug in values for Earth, right? Okay, so we know universal gravity constant, we know r because they gave it to us. If I plug in the mass of the Earth, I should be able to solve it this way. I can think of a second way to also do this, and that is this right here, right? Like if we're saying, say if it goes around like in, if we see this one revolution every 24 hours, right? Then we could also solve it that way, right? We'll try both these ways, and there might be like a way there. Wants to do this. Let's go to the mass of Earth. It's like, I think your textbook's using 5.97 times 10 to the 24 kilograms. So let's try it that way first. Okay? So say orbital speed, this would be like a tangential speed, like off the side here, called v orb, right? So like tangential, right? Is square root of gm on r, right? So we can just plug in everything there. Okay? Ooh, these problems are also good for calculator practice, right? Especially like this chapter, right? We got square roots going on. We got scientific notation all over the place. Right? These are really good calculator practice. Got 6.67 times 10 to the negative 11. Got Newton meter squared per kilogram squared. Okay. Mass there. Now they didn't actually type the mass of the Earth in this particular question, but they did say Earth. So okay, so let's go ahead and pop that in here. Okay. 5.97 times 10 to the 24. That's kilogram. Okay. Then all divided by, now this r refers to not the radius of the planet, but the distance from the center of the planet to the satellite, right? Which is definitely not low Earth orbit, right? There's different locations to put satellites. Low Earth orbit, in the big scheme of things, is it's like about 400 kilometers up. Usually you can say, well, its radial distance from center to Earth is not that different from the planet itself, but that's not the case for this particular question. Like geosynchronous, it's like way up there, right? So we're going with 4.23 times 10 to the 7 meters, right? Something like that. Okay, this is all being square rooted. Okay, so together, I got a square root. Now, you could chunk this down into smaller parts and then just say the square root to the very end. I'm gonna do it all in calculator all in one go. So I got a square root. I'm gonna open up some excess parentheses, make sure I definitely group this all together. 6.67 times 10 to the negative 11. 5.97 times 10 to the 24, and then divide by an open parenthesis. You group all this stuff together. Just two things multiplied in the denominator. Make sure it's all in denominator. 4.23 times 10 to the 7. Okay. And then remember, this model calculator automatically closes any excess parentheses for me. Okay. I'm looking at a number on my screen that says 3068, and that would be meters per second. Okay. It's probably what we're looking for. Ooh, do you guys remember low Earth orbit? How many of you guys remember like low Earth orbit or anything near the surface? About how fast you have to go to stay in orbit? Exactly. Yeah. All right. Yeah, you guys remember that? Like 8,000 meters per second about. Yeah. So yeah, I think it makes sense. Like the further out you get, you don't have to go as fast to stay in orbit, right? Because gravity field's weaker, right? So that number definitely looks reasonable, right? I think this is going to correspond to Earth not rotating exactly 24 hours, but we're about to find out. Here, as a comparison, let's say if you assume that omega is one revolution every 24 hours, right? Then what would V be from that point of view? I think this might turn out to be slightly different, but maybe not crazy different, right? So I should go one revolution is 2 pi radians, and 1 hour is 3,600 seconds. Can that give me like radians per second? Here's my radians per second right there. Right, radians per second. Right, and then I know we've done this calculation. I think a couple of times we've done this calculation. Right, 24 by 3,600. Right, yeah, this looks really familiar. It's like 727 something. That'd be radians per second. Right, but then a linear speed would be omega times r. Right, here's where you can take this number, pop it in there, and then just multiply by the radius value they give us. Okay, got 7.27 times 10 to the negative 5. Okay, that's radians per second. They told us a distance of like 4.23 times 10 to the 7 meters. 4.23 times 10 to the 7 meters. Okay. You know what's a fun question too is to say, like, can you solve for geosynchronous? Like, where would you park a satellite? That would have been a good question. Right? I think I may have asked that question or something very similar on the quiz I'm going to give you guys pretty soon. Right? You guys have a few days to do it. Right? So if it's not worded exactly like this one, there will be similar principles. You might have to use your imagination a little bit, some critical thinking. Right? But that could be a good question, right? Like if you know the rotation of the planet, where would you park a satellite so that everything? So it could be geosynchronous. Let's see what this tells us. So if we take that number times 4.23 times 10 to the power 7. Right. This one's telling us 3076 meters per second. Let's see how that compares to the other method, 3076 versus 3068. Oh, that's almost identical. Wow, that's really, really similar. Okay, I wasn't sure how close exactly that was going to be. Right. So the first way we did it was assuming we knew what the mass of the Earth was. Okay. And the second way we did it was assuming that one revolution is 24 hours. Right. It's different approaches. We got slightly different numbers, but they're almost the same thing. Right. All right. Option or not option B. Question B. Calculate the time period to go around. Okay. Well, the second method we did it, we would know what the time period was because it was baked into the assumption of right here, bam, 24 hours. So with the second method, time period just is 24 hours. Okay. Right. But what about that first method? Like assuming that you approach it from knowing what the mass of the Earth is. Because the Earth doesn't actually rotate exactly 24 hours because it's also revolving around the sun at the same time. It's like, so like making one revolution around the sun every year, you have to consider, well, that's also like getting an additional spin that you don't notice from the surface of the Earth, right? Because there's just like other orbits going on too, right? So it's a tiny bit of a difference, right? And that might be what they're getting at with this question. Okay. So this method of solving it, what would that be, right? So gotta make this connection here, okay? So if V from the first option was the orbital speed, orbital speed was like 3068 meters per second, right? Maybe I want to convert that to an angular velocity, and then from that, calculate time period, right? To do that, right? Or how about this? How about this? What if we do this the same way we did it for your centripetal force lab? You guys remember centripetal force lab? You said the orbiting speed was distance over a time period, which is like 2 pi r divided by t, right? We can do it that way too, right? Right? Because we have this number, It's gonna go right there. He told us this number, so you can stop with this. You do it that way. Okay. Let's try that setup. So what if I do 3068 meters per second? Right? You guys see there's like usually multiple ways you can approach these things, right? Is equal to, I got a 2 pi r, but in place of r, I'm going to substitute the r that they gave us, which is this number right here. The 4.23 times 10 to the 7, and that's meters. So substitution right there. Right? And then let's say we're solving for time period, right? Because again, this is the origin of this method is knowing what the mass of Earth is, right? And then saying like, well, let's see what time comes out to be, right? Guys, can I just cross multiply this time and take the speed and divide it down? Just do that. Okay. So time period is going to be, let's go ahead and rewrite this out. 2 pi times 4.23 times 10 to the 7. And that's meters. And then all divided by 3068. And that's meters per second. Right? Meters cancel. It's going to give seconds. Right. There's one last thing here. We'll get a time period that's in seconds. Ooh, seconds, right? Do you guys think we'll have to break out some railroad tracks and do a conversion here at the end? Right? So okay, let's figure out how many crazy number of seconds this is. What's 2 pi times 4.23 times 10 to the 7, all divided by 3068. Right? That is, okay, that's like 86,629 seconds. Okay. Okay, great. We got a huge number of seconds to orbit. Okay. All right, so time period equals 86,629 seconds. All right. Say there's 60 seconds in a minute. Well, let's go to hours. How about that? Okay. 60 minutes in an hour. Figure out how many hours this is. Right? Okay. So take that number, divide by 3,600. Ooh, I got a little over 24 hours. Okay. Would that make sense? A little bit. Okay. Here, that's what the math says. See that? See 24.06 hours. Right. If you like, you can subtract 24, multiply back in 60. That's the same thing as 24 hours, 3 minutes, and then subtract that 3 out, then times the 60 there, and 49 seconds. Okay, the same thing. Okay, it's really close to 24 hours. Okay. All right, you guys get that? And so yeah, a little bit different ways approaching that one. You know what I wonder too? You know what this kind of reminds me of is Kepler's third law. What if we tried it from Kepler's third law point of view? I want to try that out. Let's do that one, right? Because, well, okay, now Kepler himself just knew this proportionality, but if you bring in Newtonian mechanics, you can show this to be the case, right? Okay. Oh, yeah. Oh, yeah. Okay. All right, so let's try it. Let's solve for time period from that point of view. Now that's, this involves both the radial distance and also the mass. Distance off the map. Okay, well, okay, it's probably going to be like the first way that we did it. So that we're going to get the same answer as what we just did right here. Then we get 86,629 seconds. Let's see if I do. All right, so here's Kepler's third law. Time period is 2 pi times the square root of r to the 3, all divided by gm. All right, so that would look like 2 pi times giant square root. Okay. We're going to have 4.23 times 10 to the 7. That's going to be to the power of 3, all divided by 6.67 times 10 to the negative 11. All right. Here, I'll just throw the numbers in here. Okay. The mass of Earth I'll treat as 5.97 times 10 to the 24. Okay. I know all those numbers have units attached to them, but I'll just bring that unit out here because it's got to be seconds. That's what it's going to be at the end of the day, right? Some number of seconds. All right, so let's do 2 pi. I got a square root. Okay, you square root and all this stuff, so I got an excess of parentheses. 4.23 times 10 to the 7 closed to the power 3. Divide by, open up a few parentheses down here. I got to make sure this is all in the denominator. 6.67 times 10 to the negative 11, close open 5.97 times 10 to the 24. Okay. Okay. Now, before I hit enter, I'm going to make a prediction that the number on my screen is going to be this number right here, 86,629. Right. Let's see. 86,624. Ooh, it's real close. 86,624. That'd be seconds. All right, I'll take it. There you go. So a little bit different approaches on pretty much the same thing there. All right, number 72, asteroid. The asteroid Ceres has a mass of 7 times 10 to the 20 kilograms and a radius of 500 kilometers. Right? Asteroid, I think it's the largest asteroid in the asteroid belt. It's named, it's got to be a big one. Okay? This used to be taught as being a separate planet too. I don't know like how visible this is from Earth. You can see with the naked eye, or if you like need a telescope. Okay? But yeah, like if you go back like I think about 100 and something years ago, school kids used to be taught like this is one of the planets and sources, and eventually it was just reclassified as just a really big asteroid. Right? What's the gravity field on the surface of this asteroid? And then the next question, how much would a 90 kilogram astronaut weigh on the surface of that asteroid? All right, it's pretty good. 72. Okay. Got Ceres, this asteroid. Okay, well, has some mass and some radius, right? Okay, and they told us both those numbers, mass and radius. Oh, let's zoom out here. Okay. So, given the mass of Ceres is, you said 7 times 10 to the 20 kilograms. Interesting, they only gave one significant digit there. Your book, I think, tends to give 3. Okay. And then the radial size is, now they said 500 kilometers. Guys, when I'm running calculations, do I want to punch in the number 500 for the radius? Kilometers. I probably want it to be in what unit? Not kilometers, but meters, right? Okay. So 500 kilometers is how many meters? What is kilo? Kilo is a factor of a. Kilo is a factor of a 1,000, right? 1,000, right? Like here's 1 kilogram. I bet a dime is, well, might be a little bit more than a gram, but it's kind of order of magnitude, right? Okay. I bet this is kind of like 1,000 of these, pretty close. Right? So let's go 500,000, and that would be meters. Okay. All right, so here's our given values right there. All right, so what is the gravity field? Well, gravity field is Gm on r squared, isn't it? Right, you see that? Find where got my poster book here. Poster book. All right. Yeah, this guy standing on Alaska here. Ah, there you go. There's gravity field, right? Gm on r squared. Okay. Okay. So let's go. Gravity field is okay. So universal gravity constant 6.67 times 10 to the negative 11 meters squared per kilogram squared times the mass of Ceres is 7 times 10 to the 20 kilograms, and all divided by radius of Ceres is 500,000 meters, and let's square that. Okay, so good calculator practice here. Good calculator practice. At 6.67 6.67 times 10 to the negative 11. You guys all got calculators on your desk, so you guys are trying this out too. 7 times 10 to the 20, close that, all divided by 500,000, and then square that. Let me back up a little bit. Right? What if I forgot to convert the radius? What if I did just 500 squared? What would I get? I'd be getting a number on the screen that says 186,000. Okay, so let's just say, like for instance, if you forgot to convert the radius to meters, right? The next question, like when you get to an answer like that, is like, would it make sense for the gravity field to be 186,000 meters per second squared? Like, that would be completely ridiculous, right? That's like, we're talking like black hole levels or something, or I don't know, I think something like that. Right? So that would be an indication of, well, okay, probably messed up something, right? So let's convert that back to meters, spread that, right? Ah, that number looks a lot more reasonable. Like for an asteroid, gravity field is 0.18676, maybe I'll call it 0.187 meters per second squared, or maybe even just 0.19. You could do that because they only gave you like one significant figure on its mass anyway, so that's probably as much as you could say. Okay, 0.19 meters per second squared. Okay. What does that compare to Earth's gravity field? Well, what if I take 9.8 meters per second squared compared to that? Ooh, that's like a factor of 52. Let's round that to about 50, right? So Earth's gravity field is about 50 times more than it would be for Ceres. Okay. Yeah. So here's question A. Right. Question B is, how much would a 90 kilogram astronaut weigh? Right. You guys good so far? We got that. I bet you could jump real high on that asteroid. Okay. Right. So question B is weight just mass times gravity field? Okay. So we're going to take a 90 kilogram astronaut, and we're going to multiply it by 0.19 meters per second squared. 90 times 0.19. We're looking at 17.1. And what unit is that? Guys, it's 17 what? Newtons. 17 newtons. Okay. 17 newtons. Hey, 17 newtons. And this guy's 10 newtons. This guy's another 5 newtons. This guy's 2 newtons. This right here, right? So 90 kilograms. That's pretty heavy actually. So that might be like if you're like wearing a spacesuit and you got the whole like oxygen pack and everything, right? Okay. So if you're standing on the surface of that asteroid, you would weigh this much right here. This much right here. 17 newtons right here. Same thing. Boom, boom. Okay. Remember in the Pathfinder, I wonder if you could just like jump off this asteroid. Right? Like how fast would you have to jump? So you just like flew away into space forever, right? Would that even be possible? Isn't that kind of an escape speed question? Escape speed, right? Which really involves, we can prove this with conservation of energy, but haven't quite got to yet, right? But let's just go ahead and play this. I wonder how fast would you have to jump if you want to say, I wonder if I could jump off this asteroid. Okay. So that was question C, in my own ripping question. I think pretty good. I got the C solar eclipse. How about you? All right. Good weekends, especially 3 days. Yeah, same here. Yeah, 3-day weekends are always nice to kind of get things a little slower and recharge, get some extra stuff done too sometimes. Okay, let's do square root 2, 6.67 times 10 to the negative 11. The mass of Ceres, what was the mass of Ceres? 7 times 10 to the 20. That's kilograms. All right, and then I'll divide it by radius of Ceres, reason 500,000 meters. Oh, whoops, I forgot to put the unit here. The meters squared per kilogram squared. Okay, this is meters. Okay, and this is all underneath that radical. Okay, so again, a good calculator practice. Okay, so we're about to find out how fast would you have to jump if you wanted to just jump straight off this asteroid. All right, 2. Okay, so I got, let me go some more parentheses. Right, 2 times 6.67. 2 times 6.67 times 10 to the negative 11. Got 7 times 10 to the 20. I'll divide it by 500,000. Okay. And the answer is, right, so 432. And what's the unit? 432 what? Meters per second, right? Ooh, do you guys think you can jump at 432 meters per second? That's about 1,000 miles an hour, isn't it? Yeah, so, right, so, yeah, if you're on that asteroid, you'd be stuck on that asteroid, unless you have like a rocket or something, you could get out, but yeah. You jump as fast as you can jump, then you fall back down to the surface. Okay. Number 92, cannonball. The moon's mass is 7.3 times 10 to the 22 kilograms. Right. Oh, let's compare that to one we just did for the the asteroid series. Look at 7 times 10 to the 20, and the moon is like 7 times 10 to the 22. How much more massive is our moon compared to Ceres? It's about you guys see it's 2 orders of magnitude, 10 to the 22 versus 10 to the 20. Is that like 100 times? Yeah, I think so, right? I think our moon is, and then the 7.3 compared to the 7, so a little over, right? Our moon is a little over 100 times more massive than Ceres, right? And its radius is 1785 kilometers. Okay, again, we want to convert that to meters before we do any calculations with it. Newton's thought experiment of firing a cannonball from a high mountain or attempted on the moon, how fast would the cannonball have to be fired for it to, I guess for it to orbit, right? And how long would it take to return back to the cannon? I meant to show you guys a Paul Hewitt video. I've actually got one queued up. So let me get that up here. All right, and we are back. Here we go. Circular orbits with Paul Hewitt. Ooh, all right. There you go. Oh yeah, and there's that's what Giovanni remembered too, right? 8 kilometers per second. Now, that's for the Earth, right? And the moon wouldn't have to orbit as fast, right? It's not as massive or as big, right? But How fast? Okay, oh, that's the question. That's the first question here. How fast would it have to be? Right. Oh, it's the moon. It's probably not as fast. Find out exactly. Number 92. Right, so here's about. Right. I'll draw kind of what he drew, right? So we got the moon, right? Here, like some crazy tall mountain, right? And we're gonna like orbit something orbit around the moon, pretty much, right? Have a cannonball orbiting. Right? So here's the moon. Right? We told the mass. Here, I'll do capital M, right? Because it's what's being orbited, right? Mass of the moon is 7.3 times 10 to the 22 kilograms. Okay? And then the radius of the moon, they said 1785 kilometers. So 1785. Okay. Now that's kilometers. Okay. Guys, do I want kilometers? Do I want meters? Probably want meters. Okay. So times 1,000. Okay. So any calculation I'm doing for the radial distance, I want like 1 million on something, right? For meters, 1.7 million. Okay. Right, so here's our givens. Right? You're also allowed to know universal gravity constant, so you know that too. Right, so how fast? Right? Well, this is back to, here, I'll go ahead and rederive this. Centripetal force is being provided by the gravity force. So that's mv squared on r is equal to gmm on r squared, right? Mass of the moon, mass of the satellite. Right? So an orbital speed for a circular orbit would be the square root of gm on r. Okay. We already applied that earlier today, just rederive that. It's a good thing to be able to derive that, right? You can see like how things work, right? Where things come from, okay? But now let's go ahead and plug stuff in. So you got a big old square root. Universal gravity constant, there's your 6.67 times 10 to the negative 11 meters squared per kilogram squared. The mass of the moon, 7.3 times 10 to the 22, and that's kilograms. Okay? Notice they didn't even give you the mass of the cannonball because it doesn't matter how massive the cannonball is. Right? If it's more massive, you might have to use more energy to blast it. But here you're asked about blast speed. Right? So if you had a small next to a large cannonball, it could be going at the same speed in orbit. Okay? And then the radial size of the moon, 1785, and then times 1,000 to turn that back into meters. Right? This is all underneath that radical. Extend this down a little bit. All underneath that radical. Okay. Yeah. So you guys remember before for Earth, this number comes out to be a little shy of 8,000 meters per second. So about on the moon, it's going to be probably significantly less than that. So square root 6.67 times 10 to the negative 11. 7.3 times 10 to the 22. Right? Earth is like 10 to the 24 kilograms. Moon's like 10 to the 22. So Earth is like almost 100 times more massive than the moon. Right? Say almost because 7.3 versus like 5 point something. Yeah. And then all divided by 1785. Zip, zip, zip. See what I'm getting here. Ooh, okay. 1652. That's meters per second. That looks believable. Because remember, the Earth, this was like almost 8,000. So the moon's like 1652. Yeah, I can believe that. It looks believable. Okay. And so if you're on the moon, really tall mountain on the moon, you blast it horizontally at that speed, it'll just stay in orbit around the moon. Remember reading on the internet a few months back that supposedly some of the satellites, even from the Apollo missions back in the day, like they had some stuff orbiting the moon. They just like left it there, and supposedly like, to this day it's just still orbiting the moon. So, what else they asked here? How long would it take to return to the cannon? So how much time would it take to go all the way around once, like one revolution? How much time? Ooh, that sounds like your guys' centripetal force lab when you were trying to calculate speed by doing circumference divided by time, right? And here we're kind of doing the reverse of that because we know what the speed is. And we could figure out circumference, just 2 pi r. Okay, and then we just solve for time, right? So get that kind of rearranged, right? Okay. So I could say some like maybe okay, v orb is 2 pi r divided by t, right? So there's circumference divided by time period, okay? And then do an algebra switch around. So cross multiply the t, divide down the v. How to get the time period is 2 pi r divided by the orbital speed, something like that. Okay. So then the time period would be 2 pi. Okay. They told us the radial size was, yeah, I'm just going to use the radius of the moon itself because okay, this would be pretty close to it, right? 1785, zip, zip, zip. 1785,000, and it's a million. That'd be meters. And it's going around at a rate of, well, we just found that as 1652. That's meters per second. Okay. Oh, so this is going to come out to some number of seconds. Okay, so we might want to convert after this because maybe it'd be like an hour or something like that. So it's 2 pi times 1785000, all divided by 1652. Okay, so I'm getting a big number here, 6,789, because that's some number of seconds. Okay, let's go ahead and convert that to hours. Let's see how many hours that would be. Okay. So railroad tracks, can I say 1 hour? It's like 3,600 seconds. Okay. So 60 times 60. Okay. So divide by 3,600. I'm looking at 1 hour. Well, okay, so 1.89 hours. What that? So almost 2 hours. Right? I can believe that too. Let's subtract 1 times 60. So that's 1 hour, 53 minutes. Subtract 53 times 60 again, and 9 seconds. Okay. Okay. I want to do one more thing with this. Let's try Kepler's third law version of this. Kepler's, hey, go back and find Kepler's third law. Right, we'll do the Newtonian version of this so we can do an actual calculation, right? Okay. So supposedly we should be able to just go straight to, I mean, this just the same thing, same process that we did, it's just all substituted. So we can just solve straight for the time period, okay? In terms of, oh, they told us the mass and radial size of the moon. And we're also allowed to know universal gravity constant. So we could have just done it in one shot straight from there. Let's try that version. Let's see if I get the same thing. So time period for orbiting the moon would be, okay, so I got 2 pi times, got a big old square root. Here, I should write this way first in terms of variables. So that's what we're doing right there, right? Okay. So punch some numbers in. Told us 1785 is kilometers for the radius, so times 1,000 for meters. Okay, that's being to the power of 3. Ooh, got the number of millions to the power of 3. It's gonna blow up pretty big, right? 6.67 times 10 to the negative 11. And the mass of the moon was 7.3 times 10 to the 22 kilograms. Okay. Okay. So we got a 2 pi, we got a big old square root, got some excess parentheses here. 1785,000 to the power of 3. All divided by, and then I should really open up some more parentheses to my calculator. Make sure this is all grouped together in the bottom. Denominator 6.67 times 10 to the negative 11. 7.3 times 10 to the 22. So this is telling me time period is 6791 at these seconds. Oh, and what did I get before? I got, okay, so the way we did it before, we got 6789 seconds. And then using Kepler's third while I'm getting 67.91 seconds. That's like 1 hour, 53 minutes, and 11 seconds. Wouldn't that be? All right, so like nearly identical. There's two different ways to do it. All righto. Okay, well, I think that worked out pretty good because that's all the ones I assigned. All the ones I assigned, we've covered in class, right? So again, you guys want to hold on to those a few more days to be right? Let's have this due on Friday. I'll get you guys your quiz probably tomorrow, I think. That's right there in class, right there.